Swayam Prabha. Digital India. Educated India.
Welcome you to the next class on Inorganic Chemistry of Life Principles and Perspectives. In the previous class, I have introduced the different types of nickel enzymes, variety of reactions. I have also started going through the details of the one of the enzyme urease, which is a hydrolysis type of enzyme, where the urea is broken down into ammonia and the CO2, and in presence of water it will be H2CO3. And we were looking at in the previous class about the mechanistic aspects. Already I have talked to you some aspects like binding through carbonyl moiety. When the flap is open, the urea comes in, and then the flap turns where it binds to the other NH2 group through hydrogen bonds, the distal NH2 groups, and then you have an attack of the hydroxide moiety from the neighbor hydroxyl group that is present or that is activated by the nickel center. Now, let us look at the same as I mentioned in the previous class. There are two sets of mechanistic paths are being proposed, having some very close by kind of a similarity in terms of the intermediate. So, based on this, now in the first case that you have an enzyme in the state prior to the activity, in presence of the urea, the enzyme becomes active, and at that stage you have an open core towards for the urea to enter into the active site, and the urea binds initially through the carbonyl moiety. And then the other aspect is that, as I mentioned to you earlier, the NH2s are getting stabilized by the hydrogen bonds, and one of the group of the NH2 will be more like a hydrogen bond donor kind of thing, the other NH2 will act more like a hydrogen bond acceptor, and but overall it gets locked up, as I told you, locking up the whole thing. Now, in this particular B type of mechanism, that you have your hydroxide on the nickel, the hydroxide showing a nucleophilic attack at the carbonyl center will lead to this kind of an intermediate, and loses the ammonia with appropriate kind of amount of water, etc., form a carbamate intermediate. And this carbamate intermediate again in presence of water will break down to ammonia and H2CO3, and the enzyme is regenerated. Okay, in the other case, after the CO is bound to the nickel, when the flap is closed, it is possible that one of the this other NH2 could be coming closer to the second nickel center, and this upon transfer of the proton, you have the bridged hydroxyl group attacking on the carbonyl moiety. So, in the earlier case, it was the nickel hydroxide which is showing a nucleophilic attack here, and here it is a bridged hydroxyl which is showing the nucleophilic attack after the proton is transferred, and this gives a slightly different kind of an intermediate, and then after that the same kind of thing. So, you have one ammonia, then in presence of the water it will give back to that. So, the two possible kind of mechanisms have been proposed for these ones, but nevertheless the common factor in all these things is binding through CO and then flap closing and then followed by nucleophilic attack. Then at the end water cleaves the thing into the making the one. So, the same thing whatever I talked to you been put in the form of some points over here. So, one of the nickel binds and activates urea, and the other nickel binds and activates the water. That is point number 1. Okay. So, that is when the urea enters into the active site center or active site cavity, And there is a flap I mentioned to you, that is a mobile flap. Flap can be changing, can be turning, and that flap is the open form will now turn into the closed form of that. So, the bound urea now is stabilized by a network of hydrogen bonding, I mentioned to you that too, orienting the substrate into the catalytic cavity. So, therefore, all these units are utilized, number 1 to recognize urea, number 2 to lock in the urea both, and this one is helping in the protonation part of it. Now, urea binds at the 5 coordinated center, nickel center, and this is further stabilized by the various groups that you have. So, the other NH2 part might approach in the nickel 2 center, and that is what, and of these where the nickel and other nickel, those two are the bridge centers. So, this all these things will bring a conformational change, that means entry of urea into the closed center of the reaction center or catalytic site will be associated with the conformational changes, because the flap open, flap closed, that brings a lot of changes, and these changes will bring these carbonyls pointing towards the amine group of the urea. So, you can see again that too. So, therefore, you have the groups of the various residues, the alanine 170, alanine 366. So, all of these turn their CO groups towards the NH2, and therefore, they act as a hydrogen bond acceptors, because CO cannot act as a hydrogen bond donor, it can only act as a hydrogen bond acceptor, okay, towards the NH2. Okay. And this all helps that the binding of the urea towards the nickel centers. Now, as you know that the urea is a very weak ligand in terms of the chelation or poor chelating ligand, and because it has a low basicity, and in other words Lewis base character. And this Lewis base character has been modified by the hydrogen bonds that you have. So, these hydrogen bonds will modify the Lewis base character of the urea, and the urea binds somewhat quite okay with all these hydrogen bonds. Okay. All this will help the NH2, and it allows to bind to the nickel 2 center. So, the position of the urea in the active site, as I said earlier, is associated by structural changes, conformational changes, and this change is also included in the neighbor residues of this. Okay. So, that will turn into hydrogen bond donors as well as hydrogen bond acceptors. So, on one center you have a hydrogen bond donors, and the other close to the other nickel center you have a hydrogen bond acceptors. So, all that we need is this particular thing. So, these are the kinds of the two different types of the possible mechanisms they are present in the literature. Let's continue with what we were looking at. So, we have the urea moiety getting locked up in this particular system, where the carbonyls are turned by making this flip of this. Okay. So, essentially what we are saying is the binding of the urea molecule is associated with a number of conformational changes, and thus you have two different kinds of mechanisms. Now, there is another aspect that also is part of this particular enzyme, is that where you have the thio function which is close to the dinuclear center. As you can see from here, there are two nickel centers. The nickel center, one where you have a urea bound, the nickel center, the other one where the water can be picked by the proton, by the nearby base, which could be carboxylate base most of the times, and that could be aspartic glutamic, which will take away the proton, and then that you have a hydroxyl moiety. And now, this is associated with an SH moiety which is in close by, and this is the reason precisely why two different kinds of mechanisms have been able to provide in this particular thing. So, therefore, for the intermediate that you have here, that is the nucleophilic attack of the nickel hydroxide, and this the protonation is coming from the thio function. and this thio function is involved through the thiol function is involved in the proton, and then that will leave the ammonia and then goes back in the same manner as the other case too. In fact, there was some experiments done where in the literature people have looked at modified versions of the urease enzyme, where they have modified this SH moiety, and when you modify this SH moiety, the reaction is being basically modified or inhibited rather, the reaction is basically inhibited. So, therefore, we understand that the thio function utility is also important in all this, and that is what is over explained over there. So, essentially you have a urea and you have a hydroxyl attack on this, breaking the ammonia and the intermediate, and this intermediate further with the water will go with another molecule of ammonia and the H2CO3. So, this is up to the intermediate part and then further goes. And because breaking of this carbamate intermediate in the presence of water is a very fast reaction. Okay. So, the initial attack is the slower reaction. So, the initial attack followed by breakage of the carbon nitrogen bond of the carbon urea, that is what is the slower kind of a version. So, now we have looked at all the possible things that are there in the urease mechanism. The urea where the binds initially through the carbonyl moiety to one of the nickel, and then that drags the molecule closer to the active site, and in this process that is associated with a conformational change, and then the flap closes. When the flap closes, all the carbonyl moieties turn towards the amine moieties and then lock in the whole system, and then you have the hydroxyl giving a nucleophilic attack on this, and then in one mechanism we have used the SH moiety, in the other mechanism we have used the imidazole for proton transfer. Therefore, two different mechanisms have been postulated or proposed for this kind of thing. Okay. Now, that is what about the urease reaction. Let us look at the next enzyme is hydrogenase. Hydrogenase is an enzyme, as I mentioned already earlier, the reduction of H plus to H2 or oxidation of H2 to H plus. Okay. So, therefore, in the anaerobic microbes, they continuously convert or utilize this H2 to reduce the end acceptors like O2, NO3, SO4, CO2, etc. So, these are all reduced. So, therefore, the microbes also contain the H2 evolving reducing equivalents, and they were all utilized by these ones in terms of the reducing the protons. So, the protons have to be reduced to H2. Okay. So, there are 4 different classes of nickel ion hydrogenases, and one of them is a membrane based associated proton pumping and energy coupled type of a system, and that is what we look at in this particular case. Other other hydrogenases are mostly based on the iron. So, we are not going to look at those ones. So, we will look at the nickel ion containing one. So, let us look at the enzyme part. Nickel ion enzyme hydrogenase contains at least there are 2 subunits. One of the subunit is a large one, other is a small one, having the 60 kilodalton for the large and 30 kilodalton for the small one. Okay. And we will see just in a while in the next slide what these are and how they are. So, let us look at another aspect. This is obviously, as I told earlier, in the case of urease, the nickel enzyme expedite the reaction to 10 power 14, and in this case the hydrogenase turns the reaction to very high with a kcat by km 10 power 8 to 10 power 9, okay, with a turnover number of 9000 per second. So, it is very highly turnover kind of a enzyme. The other thing is, if you look at the enzyme, which I am going to show you in the next slide, nickel iron center is present very much deep inside. It is about 30 angstrom inside the protein when you count from the periphery. So, this means that the hydrogen has to travel to this particular site. So, as I told you, nickel hydrogenase as I mentioned earlier has two parts. One is a smaller version of the molecular weight subunit, another is a large subunit. So, you have about the 30 kilodalton and around 60 kilodalton. You can see this is roughly double. Now, so the bigger one, what you see a kind of a cluster. What is this cluster? You go this side, you will see that this cluster is nothing but iron nickel cluster. So, iron nickel cluster have got the sub binding ligands like cyanide, carbon monoxide on the iron side and the thio fragments on the nickel side, and these are all secondary interactions giving. These are all coming from the protein, and this is the actual active center or catalytic center. Now, this catalytic center cannot simply function if it does not have a proton source and the electron. Okay. So, you can see here a set of clusters, the yellow orange kind of clusters. You can see more clearly over there, these three. So, these three, can anybody recollect this? These are the iron sulfur clusters. Iron sulfur clusters are electron transfer clusters. They can take the electron and give it somewhere. They can give the electron and take it afterwards too. So, both ways, reduced form of the cluster, oxidized form of this cluster. Okay. So, oxidized form is the one where it can take the electron, reduced form where it can give the electron. So, therefore, these are the involved in the electron transfer. So, you have an electron transfer funnel and you have a the active center. This active center, if you count from the surface, this is something like 30 angstrom. So, therefore, the hydrogen which is an input for this has to travel through this particular protein by 30 angstroms and reach this one. So, this is where this kind of a nickel hydrogenase enzymes forms a kind of a tunnel structure here, which is not the main important agenda of this particular course. In a biophysical chemistry, you will look at that kind of thing, but take it as granted there is a kind of a funnel or tunnel and funnel. So, you have where the hydrogen is passing through that. And then you have a sequence of the electron transfer that I explained to you earlier when I explained to you the electron transfer by the iron sulfur clusters. Depending upon the redox potentials, they are arranged. So, you can see, and this is your nickel iron cluster. So, this is the total the enzyme configuration in that, and where this unit is attached through some interactions like the kind of a weak interactions here. So, this entire thing is associated for the activity of this, and the hydrogen enters through one of these channels which are not shown over here and interacts with this. So, let us move on here. So, just that end center alone is shown over here. You have iron center, you have nickel center. The iron has got Cn, CO, Cn. The nickel has got cysteine as another cysteine, and these are bridged by two cysteines. And there is a X bridge, it could be OH, it could be water, it could be O2 minus, etc., depending upon the situation in which the cluster exists. What situation? It could be oxidized, it could be reduced. In the oxidized one, you will find the bridging, in the reduced one, you will not find the bridging. So, in the oxidized one, you will have the bridging, in the reduced NiFe hydrogenase, you will not find that. Okay. So, these hydrogenases, okay, they have a very the iron containing hydrogenase have a very high efficiency. They can convert 5 to 10 millimolar of hydrogen they can generate per minute per microgram of the protein, whereas nickel containing hydrogenases are somewhat lower in efficiency and they give 0.1 to 0.8 millimolar hydrogen per minute per microgram. When you are looking at the H plus going to H2 reaction. Okay. So, these are the kinds of the hydrogenases that we have. How does this hydrogenase work? Let us look first at a simplistic view. Simplistic view, now we have seen in the previous slide, there are two possibilities. The two unit cells, the two subunits, what are the subunit having the iron sulfur cluster, other subunit having the nickel iron cluster. Okay. So, therefore, we will look at. So, we have a nickel in the nickel 2 form and the iron sulfur cluster in the 2 plus, which is the oxidized form, and this is sufficient in nature to accept the hydrogen, and this hydrogen will convert the nickel into nickel hydride species. Nickel hydride species can be in turn with the exchange, in this can be in the resonance forms. Nickel can undergo oxidation and this can undergo reduction. So, therefore, you have a redox between this and that can give. So, the species could be either this which can convert into this, and this particular thing will get oxidized and then remove proton. So, one proton has come here, one proton is come here, 2 electrons are come here. That means, from H2 you are taking away 2 electrons, therefore, you brought 2 protons, and that is what it is. So, important thing is nickel 2 with the oxidized iron sulfur cluster and nickel hydride in this cluster. This can be you can have a the two other the other form is nickel 3 hydride too. Okay. And this gives a kind of a EPR signal. So, the EPR signal can conform this too. So, using these information, the scientists have associated the corresponding mechanism. So, the corresponding mechanism when you are looking at, there are two parts. One part is, first of all, the enzyme is in the passive state, it has to be activated. Once the enzyme is activated, it will go into the catalytic cycle. It will go into the catalytic cycle here, you can see that. So, therefore, we have two parts. So, once it goes into the catalytic, it will continue. So, that means the enzyme is activated when the resting state enzyme is exposed to hydrogen gas for reasonably long period, then this particular species is formed a kind of hydride, and now this is an active form. So, this particular species can interconvert between this and this one, where you have a nickel 3 plus cation. So, that is what is showing the nickel signal, the EPR signal of this. Okay. And now, once you have here, there is a hydrate transfer, as you can see over there, from this to goes here, there is a hydrate transfer, and then this upon the hydrogen can split into the two, and that gives one H plus, one electron, and the next step gives one more H plus and one more electron, and this step is triggered by pulling out this particular proton by a nearby base. As you can see in the enzyme, close to this center, nickel center, you have other residues. Those residues are actually involved in taking out this one. So, that is why you have to always see not just the coordination sphere, you have to see the neighboring species too. You see that there are neighboring species of the nickel, which is aspartic, glutamic kind of thing, arginine, cysteine, leucine, valine and histidine. So, so many residues are there nearby, these are all important. Okay. So, that is very essential to look at. So, as you can see that will be that is the one which triggers the reaction by pulling out the proton and then go to the next cycle. So, you can see, so this is the kind of. So, once it gets into the active cycle, it can continue to that. So, when it goes to the passive, you require to activate by using the hydrogen gas, and this is whatever I talk is written over here, you can leisurely read and try to understand. So, we have made two parts of it. One is, first thing is the resting state going to active state, and the second part is catalysis part of it. Things are very clear from this particular. So, do not club these two in a single one, so that it will be difficult for you. So, same thing I have put in another form here. So, you have the nickel 2 iron sulfur cluster in oxidized, it was a hydrogen gas, you get this one nickel going the redox part of that, and here is the active part. So, if you are not happy with this, you can be just happy with the previous slide is good enough. You do not need to look at this particular mechanistic thing at all. There is no necessity to look at this. How do we know that the reaction where the hydrogen is interacting with the nickel center? So, people have looked at this by using the carbon monoxide in the system, and you know the carbon monoxide will bind much more strongly to the nickel as compared to the hydrogen, and then that becomes that will be stops the reaction, inhibits the reaction. That means nickel center is active, important in activating the hydrogen gas initially, and that is where you break the hydrogen gas into this. So, what we have studied, we have looked at all this information of hydrogen H plus going to H2, H2 going to H plus. One is a reduction reaction, other is an oxidative reaction. These are done by the nickel iron kind of an enzyme, and that is where the cycles of the reactions, and H2 converts to 2H plus in 2 steps, 1 H plus 1 electron, other H plus other electron, and that is what is about the hydrogenase enzyme. Now, I will take one another enzyme in this class is that superoxide dismutase, and you know that in the superoxide dismutase the O2 minus is converted to H2O2 and then just simple O2. So, this is the active site of the nickel SOD enzyme, nickel, and you see that what is the histidine part, then amine thing, and this is the amine nitrogen, and this is the cysteine. So, these are the kinds of things bondings that you have, and this particular thing, the 2 are the sulfur, 3 are the nitrogen, these are the ones which you get in this. This in presence of the nickel 2 plus, in presence of O2 minus, the O2 minus will bind at the nickel 2 plus center, and this is recognized by the this is by a group which has a proton, and when the proton is lost, it becomes a corresponding base, and this makes the hydrogen bond. So, therefore, this hydrogen bonding is a kind of a parameter which drives the reaction towards these to recognize the species, and this kind of a thing will lead to the removal of in presence of the proton, this will cleave this particular bond and give H2O2. Okay. And this upon one more molecule of the O2 minus dot or one more species of the O2 minus dot, it will be bound to the Ni3 plus, and this one and this particular thing in presence of proton again gives another O2 molecule and gives back to this. Let me once again go through this. So, you have nickel 2 center on this in presence of first O2 minus, the O2 minus binds here, stabilized by the BH. There could be COOH, other kinds of things too, could be SH, all these kinds of things, and that is being stabilized over here, and in presence of the H plus, this will give H2O2, and because you are breaking this, add proton here, break this one, that means you need to reduce, because you have a O2 minus, HO2 minus, and then you take 1 electron out into this. So, that will become. So, when you take out 1 electron of this nickel O bond, nickel becomes nickel 3 plus. The nickel 3 plus will bind to another mole of O2 minus dot, and that will again be interacted by in presence of the proton. So, you have a total structure revolving around this particular thing mechanism. So, 2 moles of O2 minus dot, which is a superoxide, is converted into H2O2 plus O2. Obviously, it requires 2 protons too, and this kind of mechanism I explained to you in manganese, etc. So, therefore, I do not need to spend too much of a time. One last thing in this particular case I would like to get to you is the glyoxylase. As you can see, methyl glyoxal is converted into lactate. So, methyl glyoxal into lactate, you see here the 3 carbon here, 3 carbon product, therefore, there is no carbon loss, carbon gain, and you can see an aldehyde, methyl is as it is, the aldehyde is converting into carboxylic acid and the CO is converting OH. So, out of this you can see one center of the carbon is reduced, other center of the carbon is oxidized. So, overall you do not see that much of a difference in that. So, that is how, and in this case the nickel is bound to this 2 waters, the aspartic, the histidine etc. You can see very nice kind of thing 1, 2, 3, 4, 5, 6. So, you have a hexa-coordinated kind of a nickel, but with 2 water molecules, and you know when water molecules are there, they can either convert into OH or they can provide a coordination by elimination. They can be easily substituted by the substrates. So, you can see that this methyl glyoxal, the converting into the other form of it, keto-enol kind of a form, by the enzyme. This GS minus is an enzyme. So, enzyme converts this first. This converted form can bind to the nickel center. So, the enzyme, a part of the GS minus will convert and this will bind to the nickel center and takes this particular conversion and goes to the lactyl with GS, and when the GS is removed as a GSH, it will go back to the lactate. Okay. So, you can see as such this is being converted by the GS minus and this binds to the nickel center, and then you have internal proton transfers etc., and then GS will break to GSH in presence of the water and give you lactate kind of thing. So, now we have seen 3 enzymes in this particular nickel case. In the last class we started with the urease, in this class we have finished the urease mechanism. We also looked at the superoxide hydrogenase, then superoxide dismutase, then glyoxylase. So, only one enzyme is left that we will see in the next class, which is called the carbon monoxide dehydrogenase. Thank you very much.